find the tangent line to each of the following at x equals 0, and then I'm given 3 trig functions. In fact, I'm given 3 sine functions, just with different things going on the inside. So I know to find the equation of my tangent line, I'll need a point on each graph. Well, when x is 0, sine of 0 is 0. And it doesn't matter what I multiply by 0 by on the inside, so sine of 0 is still 0. I'll be dealing with the origin in all 3 problems. And now what I need to do is take a derivative. The derivative of sine is cosine. And here I need to take the derivative, but I need to think about the chain rule. So cosine of 2x times 2, I'm going to write that out front because I like the way that looks better. And then the chain rule here. I'll have cosine of 1/2 x times 1/2. I'm going to write that out front. And there I have my nice happy derivatives that I need to evaluate at x equals 0 to get the slope of my tangent line. So y prime of 0, cosine of 0 is 1. 2 times 0 is 0, cosine of 0 is 1 times 2 is 2. And for the same reason, I'll have a slope here of 1/2. So let's see, I have a slope of 1 and a y-intercept of the origin, so that's just going to be y equals x is my tangent line. Here I have a slope of 2 and a y-intercept of 0, so y equals 2x. The slope's 1/2, the y-intercept is 0, so y equals mx plus b, 1/2 x plus 0. There's my tangent line. So I have y equals x, y equals 2x, y equals 1/2 x, and I think I see a pattern going on that whatever I multiply x by, whatever constant I multiply x by, it becomes my slope. And I'd like to think about why that is. So what I'm going to say is that we have a strong suspicion, a conjecture, that the slope of the tangent line to y equals sine of mx, where m is just some constant, is m. Well, let's look at the graph of a sine function and see if we can figure out what's going on visually. So let's see, I'll just graph sine between 0 and 2 pi, and then between minus 2 pi and 0. All right, so a graph of sine, just my good old sine wave, looks like this. It looks better when someone else graphs it, but this is good enough. So here I have 2 periods of the sine function. Y equals sine of x, and what we just said is the tangent line at the origin there is y equals x. All right, well, let's think about what happens when I start to think about the graph of sine of 2x. Well, I remember that rule from my algebra class that when I replace x with 2x, I squish, I compress horizontally my graph. So this point here that was at pi halves will now be at pi fourths. And I just need to keep squishing. This point from that's at pi would be at pi halves, from 3 pi halves to 3 pi quarters, and from 2 pi to 1 pi. All right, and there are my 5 key points of the sine wave compressed. Well, there used to be a slope of 1, and I compressed it by a factor of 2. Now it's twice as steep. I have the run. A slope is a change in y over change in x. The delta x used to be 2, now it's 1/2. I compressed it. All right, and I should draw the other half of my graph, seeing that compression on both sides. All right, well, let's think about y equals sine of 1/2 x. Instead of a horizontal compression, that's a horizontal stretch. Looking at my purple graph, this point at pi halves would be stretched to pi. This point at pi would be stretched to 2 pi, and the rest of the points would be stretched so far out they're not even on my graph anymore. And they're still there, I just don't want to draw them any further. And the same thing on this side. My period doubled this time. And I see that my tangent line would be less steep. In fact, I've stretched horizontally, meaning the delta x grew. And so that's a nice connection between the slopes of these tangent lines we're seeing and those transformations of functions from our pre-calculus class.